Good afternoon to all of you. This is going to be an interesting webinar based on my 36 years of experience putting together in a small, sweet PowerPoint presentation. It would go a little faster, so kindly pay attention to this because a lot of information coming in 45 minutes is not easy to absorb. You can always get a copy of this subsequently down the line so that you can go through it and keep it as in your archives for you to benefit from all the finite element analysis that you do over a period of time. How to avoid errors in finite element analysis. Before we go through this, let's look at the agenda for the day. The agenda is first we'll have a brief about AGS India, followed by essential steps while performing FEA, step-by-step guide for the validation of the FEA analysis with a comprehensive checklist to avoid the errors in FEA and best-in-class techniques for predictive FEA, and then followed with the question and answer session subsequently down the line. About AGS, our vision when we started in 1993 was engineering development through effective partnership. We try and accomplish this mission with 3 mission statements: imparting leading-edge technology through training and development, problem solving and new product development through consulting services, and providing software solutions and technical support. Our timeline is AGS started from our operations in the US in 1981. They started there, and subsequently in India in 1993. And then we moved on and started our training division academics in 97, and then established our Coimbatore operations and Trichy operations and shifted to our own headquarters in 2011. And then we have developed flagship PLM and QC tools in 23 and 24, and we are launching the QC tools now. This is our timeline over the last so many years from 1981 onwards. And the overview, we have 140-member team working out of 3 offices in Chennai, Coimbatore, and Trichy with over 2,000 customers in varied segments. Our repertoire of projects that we have done for a lot of customers helps us to augment the finite element capabilities across many vertical segments. We are affiliated with the SA India, the IMTMA. I give lectures at the IMTMA for the FEA courses, IPI, Madras Management Institute, NIQR, National Institution for Quality and Reliability, among others. Our main forte is innovation, unique designs based on cost, time, and quality paradigm that we help customers design and develop for India and the rest of the world. Our business model comprises of engineering services, which everybody knows about, specifically in the area of product design and development, dimensional management, design validation for finite elements, because that's where we started in 1993, and then value engineering and value analysis capabilities, which customers seek from us to develop low-cost products and with high-end technologies. We have been associated with Dassault Systems for their 3D Experience Solidworks platforms, the finite element tools that come with it, the Simulia as well, the PDM, and we have developed our own indigenous PLM called as the Live PLM and the Live QC tools as a flagship technologies from AGS India. And then we have been providing training for a lot of customers, starting with finite element analysis, computer-aided engineering tools, and then people know us for our GD&T and tolerance tax application-oriented training, and the DFMEA, DFM, Design for Manufacture and Assembly, and many other courses related to professional engineering functions. In this presentation, while we are looking at the finite element analysis, let us first look at where the FEA fits into in the design process itself. So when you look at the design process, we need to be compulsively looking at it from a point of view of quality and reliability as the mainstay. When we take quality and reliability as the perspective or the focus upfront at the engineering design level, then all the quality and reliability issues that would have come forth subsequently after the product has been launched vanish, primarily because they take emphasis upfront in the concurrent engineering practices that we need to put together. This is where the DFQ&R process that we have enumerated and followed upon at EGS and helped establish at many of our customer places helps to put together first-time right products and technologies. In that, what you see are the green stays, wherein you have the performance objectives, the design for performance, and the design for life and safety as the mainstay where typically finite elements finds its application. Nevertheless, it is also used in design for manufacture. It is also used in design for assembly. It is also used in the part feature tolerances to ensure that the process capability are capable of being achievable. There again, the stiffness plays a big part wherein finite elements comes into picture. Though I have given you more areas where finite elements is used, the 4 green areas where it comes of use popularly is emphasized in this webinar. So when you look at the GD&T or the product specification drawing subsequently down the line, the influential components come from both the assembly objectives as well as the performance objectives. Now remember, quality and reliability are the 2 eyes of a product. If these 2 goals are not met with, how much ever we do finite elements, at the end of the day, it is not going to be productive in terms of product success. So the emphasis when we do any finite element analysis has to come back to where they find themselves on the design process and how they influence the cost, time, quality, and reliability of the product after it has been launched. 2 kinds of finite elements we perform. One is predictive engineering. The other one is what went wrong. If we did everything according to the process right the first time, then we don't need to do what went wrong analysis subsequently down the line. Because not only is it expensive in terms of the cost of poor quality, but also in terms of reliability and the hit that comes to the brand image of the organization as a whole. It is incalculable. So when we look at this process, I want you to take home this process and institutionalize this and put this as a part of your design process evaluation so that the verification and validation are established intrinsically through the process itself. Now, the essential steps for performing FEA are quite a few, 8 of them. Let's go through them one after the other quickly. Define the problem first. When we are doing any finite element analysis, we need to ask these 5 W's. Why is this FEA required? Can we do without it? Second, what is expected outcome of this proposed FEA in terms of business benefits for the organization? Not in terms of engineering answers like, I want to look at the stress. I want to look at the deflection. No. What is expected as the outcome that will improve the bottom line of the organization? If this does not happen, the finite elements is going to be a no-brainer subsequently down the line. Third, when is the proposed FEA not applicable? In other words, the boundaries within the confines in which FEA is going to be used has to be clearly delineated. Beyond it, this is not applicable to the proposed study. For that, clarity on the functional requirement, the fit and the form of the design that needs to be validated has to be clearly told to the person who is performing the analysis. Where is this proposed FEA planned to be used down the line? Who are the stakeholders? Who are the customers who are going to consume the information and the outcome that is coming out of this finite element analysis? This needs to be clear upfront. And the last one is, which system is planned for performing the FEA? There are many systems, subsystems, standalone systems. So many things are there. Which ones are the ones which need to be critically evaluated? To answer all these questions, if you go back to the previous slide of the process, you see the one which is given in the mustard color, the DFMEA. This is exactly where we put things together. Now the DFMEA has gone through a sea change because the risk priority number is no longer going to be used. It is only the severity, the occurrence, SOD. These are the 3 things which are going to be used. So how good, how robust is our design depends on how much the FEA finds itself in the DFMEA document. In other words, unless the DFMEA document has the information, FEA should not be performed, period. Now, when we are taking the problem definition into consideration, what are we going to look at? These are the 6 headline parameters we need to concentrate upon. The first one is the data that we are going to take out of it, measurable data such as strains, deflections, stresses, frequency, temperatures, CD values, so many different things which come out of the finite element or the CFD analysis. Which are the measurable parameters? Why am I measuring those? What am I going to do with those parameters? We need to be very clear. How should we be clear? In terms of performance on life parameters. What is your sales and marketing telling in your organization about your product to your customer? Sir, this will live for a long period of time. We are giving 3 years warranty. We have 2 years additional warranty free, sir. If you want to listen to the product fit, form, and function, please talk to your marketing person when he is sitting in front of the customer. He will talk only engineering, right? So he will talk only about performance. So what are the influencing parameters in performance? How are we going about monitoring those subsequently down the line? So life, durability, factor of safety, folks, is dead. I put it purposefully on the system for you to say that any design system which is working based on factor of safety is probably over-engineered, and the company is paying for it through its nose. End of 60s, the life-based design has already come. It is over 60 years since life-based design has come. We are fighting tooth and nail with the Bureau of Indian Standards to move from factor of safety designs to life-based designs. This is what ASME is asking for. Why are we being left behind? So factor of safety may be for the safety of the engineer who is designing the product, not for the safety of the product. I will give you a simple example. A factor of safety 1 or less, you may say that the product may fail in the field, if not in your trials in the office. What about the piston inside the engine? If you put a factor of safety of 1 on the piston in the engine, your engine will consume more power than it gives usable power to the customer. 0.79, 0.8. This is typically what the factor of safety would be for a piston. Now, where does it relate to life? So life-based calculation should be the mainstay when it comes to the finite element analysis. The failure modes and effects analysis will help you to understand the criticality, the risk identification, and the mitigation factors that you need to put together. Without this, the problem definition for doing the finite element analysis is incomplete. And unless we take the cost, the weight, the time, and the quality as the driving parameters for the analysis, it doesn't influence or impact or benefit the organization. Next comes the most important thing which finite element people don't look at, but which is absolutely important. The confluence of the quality and the durability coming together in terms of reliability terms. These factors and the confidence assessment have to be the objectives for performing the analysis. If we are doing the optimization in terms of performance and cost, if we are doing the reliability calculations up front, wherein the durability calculations are intrinsically built in, if we are looking at the failure modes upfront a priori, then where is the question of value analysis coming into picture or value engineering coming into picture? Value engineering is afterthought. In the second version of the product, you're trying to increase the value or reduce the cost. Most of the people look at it, value engineering aspect as a cost engineering exercise. It's actually far from it. It is improving the value as perceived by the customer. So I'm dwelling so much upon this objective definition for the analysis, primarily because if this clarity is unavailable at the beginning, The report or the conclusions or the forward path thereof after the analysis has been completed is not going to be too beneficial to the organization or to the community at large. Next is prepare the assembly for analysis study. Component level FEA is not recommended, folks. A component lives inside an assembly. If a component is for the main means of study, look at it through the prism of assembly. Why? We have all read the Newton's laws of motion. They are all applicable for discrete systems. For continuous systems, it is the energy methods which are coming into picture. The mainstay for your finite elements through your Lagrangian approach. Your assembly has to be brought in. No single component FEA. It's of no use. So the assembly, for example, you look at the yoke here. This yoke has an upstream yoke, a downstream yoke, and a trunnion coming in between. If I am doing the durability calculations for the trunnion, I need to have the upstream yoke and the downstream yoke with the contact mechanics built in so that I can do the analysis in complete contact so that the energy is going into the entire system in which I look at the life calculations for the trunnion. If I am looking at the two yokes in addition to the trunnion as an assembly, remember, when I take the reliability calculations down the line, if the individual component has 99% reliability confidence factor, and you are putting the components together in a series as shown over here, the reliability of the assembly is going to drop, folks, as more number of components come into picture. So fewer number of components coming together, putting the system together is designed for assembly. So that has to be factored in as well. So the energy calculations, when we are putting it, only the assembly is able to reflect the true reflection of the energy going through the components in the part in the assembly, as a result of which you will be able to see the response calculations for every one of them. So if you are looking at the two yoke and the trunnion, then you have to model the next upstream component along with its pin as shown over here, so that the load path is established firmly through the assembly components. I hope I am clear. In addition to that, when we are looking at the strength rigidity assessments in the parts, we need to put this in least material condition. We rarely do that. We take it in nominal calculations. And then when we have a problem, we go back and look at the tolerances and we tighten the tolerance. Famously, I was doing a PLM audit in one of the OEMs, truck manufacturers, when the PLM head came to me and said, "Sir, I need you to answer one question. We do this FEA as a part of our product engineering upfront, and then we sign off on our trucks, and subsequently we get into trouble. And then the same FEA team performs analysis and says, yeah, there is a problem. Why they were not able to tell it earlier upfront?" This was a question asked by a PLM head in a company when I went there for an audit. Why? Because the homework was not done properly upfront at the first stage when the objective was unclear. The next is putting together the pre-stress that arises out of manufacture. As you can see, the lug bolts which are coming on the wheel, or the heat treatment, or the welding, the pre-stress that comes as a result of welding as shown in the laser torch here, or the heat treatment. Do we take into account all these pre-stresses which come into the system? Even though you have relieved it, they are still going to be there, right? Subsequently, when a failure happens, you go back and you look at the cross-section of the specimen of the failed part. Then you come back and the metallurgist comes and says, hot tires, pre-stress. Then where do we go? So this has to be taken upfront into consideration there as well. Next comes the element selection. The element should be selected based on the response that needs to be understood. If we cannot understand the response that we are expecting out of the system, we don't know the design of our own system. Folks, finite elements, as I told you, is performed upfront or post priori when a failure occurs. I would rather not do it posteriori. I would rather do it a priori. Right? So in other words, just like a patient goes to a scan and gets to know what are the problems whether there's a fracture or not. The doctor recommends a scan and he goes and does the scan to see if there's a hairline crack or not. That is only a confirmatory tool. The orthopedician is actually suspecting a fracture and is only confirming it. Similarly, you have to suspect a failure mode, estimate it, look at its SOD, and then come back and do the finite element and look for it. Otherwise, we'll be looking for innumerable failure modes like a needle in the haystack. So the choice of elements is where your signature problem comes in if we choose inappropriate elements. Beam 3D should be used only if the approximation of sectional properties is adequate to meet the stated objectives. Otherwise, get into 3D. The shell elements should be used if the behavior is for shell and plate elements, thick and thin shells according to theory of elasticity. If you do not know the thickness, thick shells and thin shells, and the transverse shear stress deformation effects, I would encourage you to look at the Motion Course book. Then comes the solid elements in terms of the brick, the pentahedron, and the tetrahedron. Typically, people use the tetrahedron quite a bit. The brick element does not perform very well in bending, especially in bending and torsion put together. Tetrahedron does a better job if it's an isoparametric element. All these things we need to know up front before the choice of the element is used. Otherwise, a picture is a picture with no meaning to it when you post-process the results. Remember, the ability to commit something to memory is available for a human being. The ability to forget something is not in the control of the human being. So when you look at a deflection plot, you look at a stress plot, you come to an inference, and then you look at the analysis and you need to correct the analysis subsequently down the line. The memory does not allow you to forget the previous image. The new one does not overwrite the previous image. So only one analysis has to be done for your inference. That needs to be correct. Next is compatibility of elements between dissimilar degrees of freedom. A lot of people don't understand this. They go and look at the stress between a beam and a solid element right then and there at the place where the interface is coming, and they look at the sweet red spot and say, oh, it's very high stresses. It is violating the Saint Venant's principle as well as the incompatible degrees of freedom, where the moments from the beam don't get transferred into the 3 translational degrees of freedom that are inherent for a brick element or a penta or a tetrahedral element. I'm giving you different examples here. When you look at the previous example, you see how nicely the flanges are modeled. Why it is modeled like that? Because we were looking for the leakages through the flanges, with the pretension coming in as a result of the assembly torquing. So the modeling has to incorporate that so that the contact pressure areas can be very clearly brought about and the contiguous zones mapped so that the leakage is prevented. Because leak is a big problem, right? Especially if it's a corrosive fluid. Now look at this picture of these bamboo sticks sitting together. These are pipes coming together. This is a part of a dryer which is 30 meters long, 3 meters diameter, rotating at 3 RPM. It is used in the cement industry quite a bit. Now the 2 bundles failed. I'm going to show you the failures subsequently down the line. People used 3D beam elements to model this. So when we did this analysis subsequently down the line to give remedial design measures for the supplier who gave this component to one of the petrochemical industry giants, he had to pay through his nose because he used the wrong element. I'm just giving you this example to show what can happen if you use a wrong element and you sign off on a report, and subsequently down the line, the failure happens and you have not captured it up front. So the multi-point constraint equations, people need to understand this, especially in advanced finite elements. What you're seeing there on the right side is a nacelle frame used in the windmill. The stiffness of the windmill structure is extremely important. This houses the generator, the gearbox, the reduction elements, everything comes inside this. So the entire unit is going, the entire load bearing structure is coming, the reaction torque is coming in here. Would I use anything other than a isoparametric element? The stiffness is very important here. The welds have to be represented, and we need to look at the weld stresses, the forces coming in, and write a separate program, take the forces, look at the three values of the forces coming in and the shear and the moments that are coming in, and then write a small program and look at the integrity of the welds, because we are not going to model weld in such huge structures. In all those cases, the grid point force balance comes into the picture. With geometries that are exploiting rotational symmetry, axis symmetric with symmetric or unsymmetric boundary conditions can be loaded. What you're saying here is the failure mode for a 210 megawatt turbine. We wrote the report and gave to the customer that in Gujarat that this turbine has lost its life. It was still running. They refused to pay us. 2 months later, the turbine failed. Developed vibrations, unstable vibrations, and they had to stop it. Get a 7 crore high pressure shaft replacement, what you're seeing, from Maharashtra State Electricity Board, spare, replace the 7 crore unit, and then bring it back online. This is the turbine. This was done over 20 years ago, not today. Life calculations. That is the power of finite elements. When we choose the right elements, put it together, you can say with confidence whether it's going to pass or it's going to fail, and in which mode it's going to fail. One of the most important things for a design engineer is not only to predict the mechanism of failure, but also to ensure only that failure mode happens and the failure does not happen in any other mode, which is undocumented. Are you with me? So what you're saying here is the failure. The customer, a Japanese, the original design was done by Japanese. And see the failure. If the correct element had been used and the contact had been put together, the flexing of the stresses would have been brought in immediately. They didn't do it. The support where the problem was. So any element should be capable to capture the deformation modes anticipated with the flexibility represented adequately in terms of the stiffness, which could be axial, bending, torsion, in-plane, membrane, any combination of this. The mass elements used for non-structural parts, ignoring the stiffness contribution in cases where the body loads due to such parts are to be considered. Next comes control the element distortion. No point in just putting, I used beautiful elements. Yeah, are the elements really beautiful? Is the picture really beautiful? Warping creates all kinds of problems. Today, the preprocessors in finite element tools helps you to overcome all these. But are we doing this? When we are in the process of applying the loads and boundary conditions, concentrated force should be eliminated from your shell elements and your solid elements. You can use it for one-dimensional elements like beams and trusses, no more. Why? They are applied over a zero area. Stress is equal to load divided by area. What is the area at which the knife edge load comes in? Almost zero, right? It affects your Saint Valence condition, and it affects your work done. Potential energy equals internal energy minus work done due to the external forces. The work done due to the external forces calculation is wrong. If you use surface loading, body loading, it is a surface integral, volumetric integral. Much better. You see where the energy gets frittered away and doesn't really go onto the system effectively, giving wrong results. This is where we need to be circumspect about it. The loads and the constraints should be far away from the region of interest to prevent their influence. Saint Valence principles, guys. we have reviewed reports of a lot of finite elements that people have done, and this basic function gets violated on and off all the time. Constraints are of three conditions: under constrained, over constrained, exactly constrained. Exactly constrained helps you to serve the purpose of the objective. The other two, far and few between. Initial boundary condition could even be energy. You look at this example of an extreme deformation taking place in a jelly. What you are seeing over here is the initial boundary condition being potential energy. When you drop an object, you just drop it in free falling gravity. Does it have an initial displacement, initial velocity, initial acceleration? No. What does it have? It has initial energy. So if you give initial acceleration, initial velocity, initial displacement, it is wrong. You have to give the potential energy and allow it to go for a free fall with gravity turned on. Otherwise, your deformation is not going to be correct. Use it for helmet impact analysis, tire impact analysis, so many different places. Energy principle. This is what we need to bring in. And the contact has to be established. Contact boundary conditions have to be very clearly defined. Node to node, node to surface, or surface to surface, which is preferred. Now, remember when we give contact and we don't give friction coefficient, you are having two polished surfaces, one can slip on the other. But in reality, in the assembly, you are going to have friction as well. But when you bring in friction, it is non-conservative. So first do it with one and then get into the nonlinear geometric modeling and then put the friction and see the influence, how bad it is, how good it is, the damping of the contact, all those things you can model beautifully. Today's systems are available so beautifully that you can predict it very nicely with very powerful tools. Thermal effects can be considered in the linear static by superposition. Assembly pleat torques need to be brought in with a self-equilibrated approach. The contact boundary condition should involve frictional effects, as I told you earlier. There's an example what is shown over there with the self-contact. So once you have applied this, then you specify the material properties. What you're looking at on the right side is actually a Mooney-Revlin calculation for a tire. One of our customers was not able to solve the problem primarily because he was not able to get the Mooney-Revlin constants from the test data for the elastomer. And the same, he got the properties, he got negative Mooney-Revlin constants, he could not solve it for more than a year. And he called the support of the software, and the software people said that no, it is an input error in your material property curves. I contacted the tire manufacturer for doing a finite element analysis on a wheel. And I told him, I will give you your tire data. I'll give the wheel data to the wheel guy. Confidentiality is assured. Let's sign an NDA. I'll do it. He gave the same property to me. And 3 days later, I gave him this inflation. He called me and said, Natarajan, I gave you the file. I'm not able to solve it using such a sophisticated tool. You have solved it. How you have solved it? Oh, that is Mooney-Revlin negative constants. That's what is the problem, right? He said, yes. I said, go back to the basics of what Mooney-Revlin does. Then you will get it. Negative slope cannot be there in your curve fit. So unless we understand, we should not use the software like a machine operator. We should understand the theory behind it and then put it together. In this particular case, the sealing of the tubeless tire happens because the air gets trapped between the tire and the rim. Pascal's law, equally transmitted in all directions, effectively seals it. So how much is the air entrapment there will help you to affect the sealing on this. This is the study for that. While performing analysis, choice of direct or iterative solvers. I've seen people using direct solvers and iterative solvers, and sometimes it takes a huge amount of time to solve. Why? Because the model is ill-conditioned. Singularities are there. That is the reason. On the right, what you are seeing is a testing of a 350-ton crane. My customer said This is the support structure, Natarajan. Can you please evaluate this and tell me whether this is going to live or not for this 350 one-time loading? Normally, I would have done it and I would have said, it's okay, we can do it. But the problem was he was cutting costs. So the support structure was fabricated from already used structural members. These members were fabricated from scrap. So he wanted to know whether this will withstand. Imagine the fear that will be there in the finite element analysis guy, because he does not have the history of the material property of this particular unit, how much life has been consumed. So we did this and I overrated it for 600 tons because it's a one-time effort. He already had the scrapyard with him. And when he came up with it, and I told him, after doing all the analysis, I came back and told him, gradually improve the loading, do it slowly. Over a period of time, people from SAIL were coming, Steel Authority of India, for checking this crane. And I said, gradually do it, move out of the way, don't come in between the girder and the support in the span area. Move out of the way, and before you start this analysis, before you do this experiment, first break a coconut in front of Lord Vinayaka. The person laughed at me. He said, why? I said, that is the factor of safety I am giving you for the already used up life. And then we put this together, and the whole day I was at home. Why? Because I was waiting for the call. The call didn't come. I knew the test was through. At 5:30, I gave a call. He said everything went through fine. I said, did you by any chance have any kind of a noise in the system? He said, yeah, in the lower two angles that you're seeing at the bottom. He said there was some vibration there. I said, that's the first local buckling mode. I had that captured. So I wanted to verify it with him. That's how you go about doing it. Imagine performing an analysis in these kinds of life and death situations. So this was commissioned by Steel Authority of India subsequently down the line. So you need to look at in-plane effect. You need to look at the grid point force balance. You need to look at the strain energy norm to ensure that the stress that you have got is actually a converged stress. Your stiffness matrix ratio has to be between these two. If you use millimeters, check the reactions, guys. And if it doesn't tally with the original within 2%, go back and look at where your model is leaking. Check for errors and warnings, and your mass has to tally within 2 to 5%. And then post-process your FEA results, compare the deflection against manual calculations. Manual calculations have to be there. Verify tension and compression regions, plot the strain energy norm to ensure that it's a monochromatic plot, and then look at the assessment of the stresses against the estimation. For example, the fasteners in the preload in the system. Go and look at the values, make sure that the load has gone through properly, and then look at it. What you are looking at on the right side is actually a hydrostatic analysis on the seal. It's a deformation based on a follower force, where the force and the geometry, normal to the geometry all the time, the geometry changes because of the applied loading. Then comes post-processing of the results. Do not violate the Saint Venant's condition. What you're seeing on the right is actually a German design, where the design failed miserably. He had given a warranty of 10 years and it started failing on the third year. I happened to be there at the customer place and I said, this was a classic case of factor of safety design versus life-based designs. You know what he said? We Germans do factor of safety designs. He told that proudly. I said, well, start doing life-based designs, otherwise pay warranty costs. This is a classic failure. And then he came to my room and he said, how do I get over it? I said, you have to replace the component. And this is how you have to redesign. Each shaft costs 12 lakhs. Imagine replacing 72 shafts in a polyester yarn plant. So check the mass, the self-weight, the reaction forces, the tension and the compression in consonance with the deflection animation, stress assessment in the known components. Symmetry of the structure should be exploited as much as possible in terms of loads, the geometry, the boundary conditions, etc. Why do I say that? If you go back and look at a full model and you get an unsymmetric thing, For a symmetric model, you have a problem with your analysis. These are all small checklists, guys. Structure subjected to internal pressure loading should not have reactions in absence of self-weight considerations. Manual calculations involving stress concentration factors should be compiled against FEA values. Sudden stress concentration or escalation should be backed by sound engineering judgment and reasoning. The relied upon results is wrong unless it is proved by engineering judgment. Increase the mesh density in the direction of the stress gradient and ensure that the stress monitored at the location does not change by over 2%. Then it is converged. Strain energy error norm should be a monochromatic plot. Do not believe any analysis results unless you have gone through this. Use H and P combination. Hierarchical finite elements is what people use. Polynomial finite elements you can use for rapid convergence. Use a combination of these two to arrive at accurate results. What are the errors in finite elements? The discretization errors, the numerical integration errors, the floating point operation errors, the shape function errors, the assumed displacement field based on that, the modeling errors, the constraint errors, and the assumptions that violate the laws of physics. We need to pay attention to these as much as possible. So to perform an FEA, error-free FEA, verification of the FEA requires adoption of a process as given earlier. Measurable parameters should satisfy the laws of physics. Output from the software is dependent on the input provided along with the process adopted. Consistent accuracy and precision require due diligence at every step of the way. And then FEA is a confirmatory tool during design, and it's a diagnostic tool during failure analysis. You take a choice whether it has to be a confirmatory tool exercise or it has to be a diagnostic tool exercise. If you are in consulting and somebody comes to you for doing a diagnostic work, it's money for you. If you are in OEM and you're developing a product, you better be on the confirmatory side, not on the diagnostic side. That helps you to take you to the end of this presentation, which was a brief one. We have gone through many of these slides. Take them, chew the cud, and digest it over a period of time. And I'm leaving the floor open for any questions that you may have in the chat box. Kindly put them over there so that we shall be glad to address them. How do I keep the value of merged cells in each cell in Excel? Say, I'm working on construction equipment. Now G load has to be used. Now G load value can be used for thing. See, when you are working in construction equipment and the mainstay is the mainstay for it is your see, I showed earlier that when you are looking at every component, look at the stress in the component individually with the nodal averaging in that component, not across the components. Across the components is valuable in certain cases, but not in all cases. In most of the cases, you output the values. Even though you have merged the values, you can plot the stresses for the element within the part. Use that and do your decision making. Fees for FEA depends on the nature of FEA. I'll ask my business development team and my technical team to get in touch with you to see what kind of requirements you have and see how we can address it. Any other question? How do we apply torque loads for robot pedestal? See, torque loads typically have, any torque loads that come on like fasteners or any other places, you apply it you go back to your fundamental equation, which gives you the inclination ramp equation, where you include the friction and you come up with the value. There's a simple calculation that can be used, and you put that value and you give the axial force as pressure in the fastener areas, contact areas, extensile on the bolt, compressive on the flanges, if you are doing a micro analysis, and then you go about putting the axial force. But if I'm looking at a macro analysis, Micro analysis, you do this. Macro analysis, if you are looking at, then I would use AE alpha delta T, temperature difference. Use that and apply the load according to that. How to validate welded joints? Do we need to mesh the weld model or any other approach? Two approaches are there. If it is a macro, you take the grid point force value, you write a small program outside, look at the values, go through your T by root 2 calculation at the root thread based on the sizing of the unit, and then you'll be done with it. Or you model the analysis. If it is going to be a persistent problem, you want to really model the FEA, the pre-stress and things like that, go the whole 9 yards. Put everything together and do a beautiful analysis, depending on the nature of the analysis. Which book would you recommend for learning FEA? Good. There are many of them. Robert Cook is one. Chandru Patla Balragundu is one. PhD FEA Professor Rajshekhar's book is one. Robert Cook is what I would recommend. Is it 3G load test will be enough for FEA for construction equipment? No. That is, you are going back to the factor of safety calculations. No. Go through cycle duty loads. Look at what kind of service loads that are coming into this. Put a heuristic model together and then come back and look at it. We had a case where a sulfur plant fell through because of a factor of safety calculation. Luckily, nobody was killed. This was in Dubai. They called us and asked us to do the analysis, and I said, what is the life warranty you want? They said 25 years. I said, okay, go ahead and show us. No, you please come and see the failed thing. I said, I don't need to see the dead body. You send me the drawing. The failure mode is already told by you. The answer is already at the end of the textbook. So I need to avoid that. I avoid that answer. That's all. So we put it together. Even today it is running. This is more than 10 years old. How closely we can achieve drop test result in any software tool, folks. When we did this test for a helmet, industrial helmet, how close to draw? See, it is all energy based. So when you are looking at, you map the amount of energy and you look at how much amount of energy is absorbed by the helmet or whatever drop test equipment you are doing. If it goes beyond a certain threshold value, then you need to provide mechanisms for release of energy by deformation. In other words, something fails as a result of which your original product is protected. For example, when you open the door of a car, in the hinge, you have a small shear pin with a hole in it. Why? When you open it fully with a bang, that pin will fail, not the door or the door. That's called as a sacrificial element. For that, the energy method has to be done. How can we check the modal analysis? Good. If you are looking at frequency, it has to be within 1% of measured frequency values. Otherwise, your analysis or your physics understanding is wrong. We had a case where the customer was measuring the frequency. If you are measuring the frequency, you need to use mass matrix, which is lumped mass matrix. If you are looking at mode shape, then it has to be a consistent mass matrix. And then you do a model assurance criteria. There are many things available in that. So a lot of things is dependent on the nature of drop test that you are looking at. You have highlighted it. I'm not able to see what it is.
Yeah.
How to avoid errors in hyperelastic material analysis? The first thing is you do the hyperelastic material analysis for a coupon material. You would have taken the material, you would have taken the data for that material, right? Simulate that exact condition first. Then apply it to your product. You will go through the whole 9 yards. Is it possible to calculate life for all components used in the product? Absolutely. Absolutely. In fact, life-based designs is what we need to go with. How to calculate weld joint efficiency. Depends on the nature of calculations. You can take the input from your finite elements and use it in your spreadsheet calculation or a separate weld formula, this thing, or use products like FE-Safe, which is available, where you can put it through the pre-stress and you're seeing it. You said that assembly level loading conditions are preferred. Some researchers use the submodeling analysis. Yeah, you can use the submodeling analysis if it is for the linear superposition approach. For non-linear, forget it, no way. For linear, yes. you can use. That's you in the earlier terminology. It used to be called as super elements. We used to use it for buses all the time. Today, you don't need to do it. You can use this. Submodeling has its own, it depends on which way you are doing the submodeling. If the displacement field is not contiguous, then you have a problem. What is the difference, major difference between rigid loads and distributed loads? Work done, folks. Work done calculations will be wrong otherwise. A single plate can be analyzed in case of a bone plate with a lattice structure. I need to see the structure to look at what it is and then look at the failure modes and then give you the methodology to meshing topology and the elements to be used to capture the deformation modes or the strain modes. Especially if you're looking at the blown plate, if it's the fixing plate inside, there it is not the question. See, the problem is there the failure mode is on the bone. If I have understood your problem correct, see, you have a bone plate. The bone plate should not lead to the bone fracture, because the bone is a brittle element. So there it requires a detailed material modeling with a symmetric or an unsymmetric material matrix, so that may be a little different. Yes, you will get the recording of this session. When the product is across the yield, then it goes into plastic region, right? Then why we perform nonlinear? I love you for this. We perform nonlinear analysis where failure has to be done in a particular manner so that subsequent components don't fail. When I'm looking at, there are nonlinear analysis. See, you are looking at only at steel. What about foam? You're taking your pump, you're putting it inside a thermocol, you're putting it and you're doing a drop test. You don't want the pump to fail. You want the thermocol to absorb the material. Thermocol material does not have linear properties. What would be the suitable element for plastics where, folks, element-wise, it depends on the deformation mode again. But if you are looking at plastics, please don't look at von Mises criteria. That is only for ductile yielding, not for brittle fracture. Can we use FEA for flare combustion systems? If FEA is a numerical procedure, the numerical procedure can be used in either an implicit formulation or an explicit formulation. Okay. And you can gather the results the way you want it. For flare combustion, I need to look at what is that you're trying to, what is the outcome of the study. Then based on that, I would be able to help you to understand and do a simulation. Is it possible to do analysis of bolted? Absolutely, yes, it can. It is possible. Depends on the nature of the. You don't need to do it for all the bolts. For some critical bolts, you can do it. At what condition shall we use RB2 and RB3 elements? Oh, Nastran. RB2, RB3 elements are nothing but they are not rigid elements. They are basically multi-point constraint equation elements which are in Nastran. The rigid element is typically a high stiffness element. RB2 and RB3 are slave elements, and there are different ways. See, in automotive structures, we use it for a lot of different applications. This by itself would require one-day class. But make sure you use it where Saint-Venant's condition is not violated. How to check the motion analysis? See, motion analysis is typically kinematic. That comes from rigid body dynamics. How to calculate? Okay, I'm coming to that. Motion analysis is kinematic analysis. Finite element analysis is flexible analysis. If you want to do finite element flexible analysis, there are special codes available where you can do it. Either in Simulia, you can do it, or some other codes are available. You can use that to simulate it. And we use these kinds of codes to do these kinds of simulations. So you let us know what kind of work it is. We will advise you how you can go about. How to calculate wear, contact, Hertzian stress. Based on what? Based on contact pressure, coefficient of friction, temperature, the contact area, the sliding velocity. So many aspects are there, and you have to come up with a contact model subsequently down the line. I had high stress and distributed connection over the rigid connections. Is it correct? In SolidWorks, it depends on whether it is away from your area of requirement. If it is within the area of requirement, assembly modeling you have to do. What are the pre-stresses one has to consider for varying pre-stress due to casting solidification, folks? Absolutely, you can predict hot tests today using finite elements. You can give the pre-enthalpy as the initial condition, and you can solve it in a nonlinear thermal model. It's an established process. You can do it in any code. You need to do it. What is the need of mesh quality checks? The need for mesh quality checks is the strain energy integration, if it is okay or not. If the integration is going to introduce noise into the system, more energy is being consumed by the system in terms of expending the energy as compared to the deformation modes. That's why you need to check it. Can you suggest failure theory for plastics? Again, depends on, I would use maximum shear stress theory or maximum strain theory or maximum shear strain theory, depending on the nature of failure. Any questions? Any other question? I encourage you to come back. I've already answered all this. I encourage you to write to us on info@egs.co.in if you have any questions or any problems that need solution, or you have a new product development and you are a little fidgety about the warranty and the life of the product subsequently down the line. We look at it holistically through the DFMA as we have put the process together, or you are looking at training or you're looking at software, any which way, you can contact us for any one of this. Folks, this is a series of design without errors that we are starting with this month. Every month, there will be a completely different topic on how to avoid errors in design. So this tagline is called as design without errors. Use this tagline, put this on your Twitter or whatever, Instagram and things like that. And we are all young engineers. I'm 58 years only. Okay. Whatever design problems you have, get in touch with us. We would be happy to help you to solve your problems. We are here to solve your problems. And we sincerely want to take this time to thank you for having attended this program among your busy schedule. I am already running late. It's a machine supporting structure vibration study. Yes, we have done. In fact, we have done a full VMC. We have done completely a full VMC for a particular special purpose machine, which they were introducing into the market, and we were able to pinpoint the vibrations in the bearings in that particular case, and we have done it for grinding wheels and things like that. So many places. Yes, we will share you the contact. Our Mr. Libin will get in touch with you, and he will give you the information. You can take it forward. Thank you very much. Thank you for your time. Have a wonderful weekend. And let's work together to develop a better India.
So thank you for the webinar, sir. And thank you for participants for attending this webinar. And we hope this is useful in your day-to-day endeavors in developing better products and technologies. Please follow EGS India on LinkedIn, Twitter, Instagram, and YouTube to access gainful information on emerging technologies in design engineering. Thank you for everyone. Thank you for your time and presence. Thank you.